Let me quickly remind you what we did towards uh, what we did in the last lecture. I believe we started our lecture by recalling the correct order of operations. Then I gave you the definition of a terms. We learned how to compare two terms in form of whether they are like terms or unlike terms. We also learned what do we get if we try to add n plus 1 unlike term in the same variable together. We get expression called polynomial, right? So next question was, what if two or more polynomials are given to us? If two or more polynomials are given, then we certainly can add them, subtract them, multiply them, and divide them to get a brand new polynomial as a result, right? If you remember, towards the end of the last lecture, I showed you a couple of examples demonstrating how to add, subtract, and multiply two polynomials, right? And we ended our lecture with a very interesting remark saying that division of two polynomials requires the concept of factorization, right? So let's begin today's lecture with that particular remark that division of two polynomials requires knowledge of factorization, and of course we would like to understand how to handle factorization. All right, so let's recall this idea. All right, so factorization is something that we will be using to divide a polynomial by polynomial, and we are going to learn the factorization process in three simple stages. All right, and you will have to apply these three stages in this order only. The order that I am going to give you, that is the exact order that you need to follow in order to factorize the polynomial. Understand that factorization is a crucial part of this course. You will be factorizing many different polynomials throughout the end of the term. Throughout this semester, we will be using this concept. So I recommend you guys to practice as many problems as you can of factorization. Okay. All right. So what are these three stages? Let's talk about them. All right. Stage number one, look for the greatest common factor, if there is any. So if polynomial is given to you and you are asked to factorize the polynomial, the first thing you need to check if there is a common factor between all the terms of your polynomial. If there is a common factor, you would like to pull that common factor out. All right, and that is really a simple strategy. There is no trick there. If I give you polynomial with only two terms, right, all you have to do is find out what is a common factor between numbers, what is the common factor between variables, and whatever that common factor is, greatest common factor is, you pull that out and you get the factorization. Now, let me mention here that there are many different factorization techniques exist. As far as this course is concerned, we will only deal with three factorization techniques, right? And I'm going to give you these three factorization techniques in three stages, right? Of course, this is the first stage. Look for the greatest common factor and factor it out, you get the factorization. All right. Stage number two, this is the spatial one and the one that you will be using repeatedly in this course. All right. Factorization of the trinomial of the form ax square plus bx plus c. All right, where a, b, and c are numbers. You can think this as a as a particular example. I would say consider something like 3x square plus 5x plus 2. A is 3, b is 5, c is 2. It is a trinomial. All right, so trinomial It is a polynomial with three terms. All right, so this is the trinomial. And I'm going to show you how to factorize the trinomial. So we are going to discuss a general idea first. And this general idea might sound little tricky, but trust me, when you see the examples, you will realize that it is indeed very simple process to implement on any trinomial. All right. The only reason why I divided it into few steps is just to give you a logical, procedure that you need to follow. All right. So here are the steps of factorizing trinomial of the form ax squared plus bx plus c. I also would like to remind you the statement I mentioned last time. Remember, the leading term and the constant term. These are two main terms of the polynomial, two important terms of the polynomial. If you know these two terms, you more or less can answer any question about that polynomial. All right. So I'm going to start my computation with something from the first term and the constant term. Look, I want you guys to compute the product of leading coefficient and the constant term. Compute the number a times c. All right. So first step is very simple. Compute product of the leading coefficient and the constant term. Right. Step 2. Find out all factors of this number AC. And out of all those factors, pick the one whose sum is exactly same as B. All right. So again, find out all possible factors of AC. Remember, AC is a number, right? Product of a leading coefficient and the constant term. This is going to be a number. You want to find out all possible factors of this new number AC, and out of all these factors, I want you to find out the factors whose sum is same as B, which is the coefficient of middle term, right? So that is the second step. Find the factors of AC whose sum is B. All right. You may wonder that what if we don't have any factors of AC whose sum is B? If that is the case, then you need to move to the third stage. All right. Meaning this idea will not work there. All right. You need to go to the next idea of factorization. Okay. Once you get factors of AC whose sum is B, I want you to break the middle term Bx into two like terms based on its factorization. All right. So rewrite the middle term Bx as its factors times x. So I'm converting three-term expression into four-term expression by simply breaking the middle term into two like terms. What I want you to do next is group the first two term, group the last two term, and take the common factor out. So we are indeed doing the common factor idea here as well, right? When you take the common factor out from the group of first two and last two terms, that will result into two terms only. Between these two terms, take the common factor out and you get the factorization of the trinomial. Again, as I said, this general idea might look little tricky, but trust me, when you see the example, it will make complete sense. All right. Compute product of leading coefficient and the constant term, AC. Whatever that number is, find all factors of that number. From all of this factor, pick the one whose sum is same as B. And then break B of x, Bx, in form of these two terms in terms of the factors of AC, right? You get four terms, group the first two, last two terms, take the common factor out, and then take common factor out one more time from the resulting two terms, and you are done pretty much, right? So this is the general idea. And as I said, once if it looks tricky right now, if it sounds tricky right now, Trust me, it will be very, very clear, crystal clear once you see the example. Once you see the implementation of this process, it will make like complete sense. All right, stage three. If we cannot use stage one or two, common factor is not there, we cannot find factors of AC whose sum is B, then we need to try this third and final stage, which consists of spatial factorization formulas. Now, I'm not saying that this formula is applicable if first two method don't work, right? This is just one technique, right? So if this formulas does not apply as well, then we declare that the polynomial is non-factorizable. As I said, there are other techniques exist to factorize them, but as far as this course is concerned, we are only focusing on these three techniques. All right. So this is a group of formulas that one can apply to factorize the polynomials, right? The first formula is the one that we will be using the most. Difference of two squares. A square minus B square. It factors as A minus B, A plus B. All right. So again, this is the formula that most of you must have used many, many times in your high school, right? This formula is called difference of two square formulas. Believe me, you will be using this formula frequently in this course as well. This is the most important formula. If there are only two terms in your polynomial and both terms can be visualized as a squares, right? Difference of two squares, then you can use this formula. The second and third formulas, they are called perfect square formulas. If you have a trinomial in the form a square plus 2ab plus b square, its factorization should be a plus b the whole square. Look, I take one thing from each term. Square root from the first term, which is a, sine from the middle term, which is plus, and then square root from the last term, which is b, the entire thing square. This formula is called perfect square formula for trinomial. And trinomial has to be in this format, a square plus 2ab plus b square. There is one more formula that is a perfect square formula. If you have a square minus 2ab plus b square, its factorization would be a minus b the whole square. All right. So again, these are two formulas that are called perfect square formulas. I use the word trinomial, right, for the left side expression. So you may wonder that can we factorize this type of trinomial using the stage 2 technique? Answer is yes, absolutely yes. So the technique that I discussed in stage 2 is applicable for perfect square formulas as well. So technically, if you don't memorize this formula, that's perfectly fine. If you know how to apply that uh, trinomial factorization method, right? So far we have difference of two square factorization formula and then two perfect square formula that also can be handled using stage 2. I would like to give you two more formulas here. Difference of two squares and difference of two cubes and sum of two cubes formula. First, sum of two cubes formula. A cube plus b cube. It's factored as a plus b, a square minus ab plus b square. All right. So if you realize that you only have two terms in your polynomial, right? And if both of this term can be seen as sum of two cubes, if you know the cube roots of both of these terms, then certainly you can use this factorization formula to factorize it. A plus b, a square minus ab plus b square. And then the last but not least is difference of two cubes formula. If There are only two terms with negative sign in between, and both terms cube roots are known to you, then you can use the last formula. A minus b, a square plus ab plus b square is the factorization of a cube minus b cube. All right. So these are all three possible techniques, all three techniques that we are going to use to factorize any polynomial. You may wonder that what if none of this technique helps us to factorize the polynomial? If that is the case, then we declare that the polynomial is non-factorizable. All right. So if none of this technique helps, if no common factor, if I can't factorize the trinomial, if I can't use special factorization formulas, then I would declare that, this is a non-factorizable polynomial. Now, I would like to give you series of examples here. This is example number 6 and 7 from first lecture's handout. All right. I'm going to add few more simple examples in here to make the idea very clear. So let me go to the board and let me show you how to solve these two problems. All right. So let's start with number 6 first. All right. So for number 6, I have two problems in here. I have two sub problems. Let me add one more to it. The first one is I would like to factorize 3x cubed minus 9x squared. All right. So this is the first polynomial that I would like to factorize. As I said, I would like to add one more problem into this problem number 6. Let me give you this one. X squared minus x minus 12. And then I have this problem, 8x to the 4 minus 4x cubed minus 12x squared. Okay, so we would like to factorize this three polynomials. Remember, we have only three techniques. Look for the greatest common factor, factorization of trinomial, and spatial factorization formulas. I would like to write down spatial factorization formulas, let's say somewhere here. All right. These are the spatial factorization formula. A square minus b square factors as a minus b, a plus b. A square plus 2ab plus b square. This is a plus b the whole square. A square minus 2ab plus b square is a minus b the whole square. A cube plus b cube, this is going to be a plus b. A square minus ab plus b square. And then a cube minus b cube, a minus b, a square plus ab plus b square. All right. Okay, so let's start with this example. I would like to factorize this polynomial. All right. So look for the greatest common factor. There are only two terms, right? I need you to find out the common factor between numbers first. Between 3 and 9, the common factor is 3, right? Between 3 power of x and 2 power of x, x square is the common factor, right? So altogether, the common factor between these two terms are going to be 3x square. I want you to factor 3x square out. Let's do that. I factor 3x square out. All right, write down leftover from the first term. 3 is being taken out as a factor. 2 power of x is being taken out as a factor from the first term. That leaves us with 1 power of x in the first term, right? So 1 power of x is left over in the first term if you pull out 3x squared as a factor. If you factor, if you pull 3 as a factor out of 9, left over is 3, right? And then if you pull x squared out of the second term as a factor, left over is 0 power of x basically. So it's just 3 left over in the second term. And that's it. This is a factorization of that polynomial using the first technique. Indeed, a one-line example, right? Pretty simple and straightforward problem. There is no trick there, right? So look for the common factor, greatest common factor, pull it out, and you get the factorization. All right, let's go to the next one. X squared minus x minus 12. As I said, this example is not in your handout, but I really would like to discuss this example because it will help us understanding the next problem. Okay. All right. So looks like this is a trinomial. Check for the common factor. I have 3 terms, 1, 2, and 3. Between numbers, nothing common, right? Between power of x, nothing common. Meaning that this is a trinomial that does not have any common factor, right? I can move on to the second stage. Can I factorize it using the trinomial factorization method? Let's check, all right? I'm going to compare this with ax squared plus bx plus c. And I would like to have the values of a, b, and c. What is a? A is the leading coefficient, right? A is 1, b is negative 1, and c is negative 12. All right, so I got the values of a, b, and c. Now let's apply that step-by-step method. Multiply the leading coefficient with the constant term, a times c. I get negative 12. All right, so first step is done. I got the product of, leading coefficient and the constant term. It's negative 12. Second step, the most important one. Find all factors of negative 12. Let me write down all the factors of negative 12 carefully. All right. If you multiply negative 1 by 12, you get negative 12. One of the factor needs to be negative in order to get negative outcome, right? If you multiply negative 12 with 1, you get negative 12. If you multiply negative 2 with 6, you get negative 12. Or negative 6 with 2, you get negative 12. If you multiply negative 3 with 4, you get negative 12. Or negative 4 with 3, you get negative 12. These are all possible factors of negative 12. All right? I found out all possible factors of negative 12. Which one should I choose? The one that I need to choose must add up to negative 1. So I'm going to check what is the addition of all these factors carefully. Sum of negative 1 and 12 is 11. This is not negative 1. Sum of these two is negative 11. So I cross that one out too. Sum of 6 and negative 2 is 4. I'm looking for negative 1. Sum to be negative 1, right? Negative 6 plus 2, that's negative 4. That's not same as B. Negative 3 plus 4 is positive 1. You want negative 1, right? And sum of negative 4 and 3, this is negative 1, right? So this is the factors. These are the factors that I was looking for. All right. These are the two pieces of negative 12 whose sum is negative 1. All right. So we are done with first two steps of that general idea. I computed product of A and C. I found out all factors of A and C, and out of them, I choose the one whose sum is really negative 1. Now, the third step. I'm going to write down that third step here. I will start with, the problem itself. So let me copy this line, okay? X square minus x minus 12. What I said was following. Break the middle term into two pieces based on those factors. So my goal is very clear. I'm going to convert this three-term expression into four-term expression. I will write down that negative x as a sum of two like terms. Look, negative 4x plus 3x. If you add them, you get negative x back, right? So we are not really doing anything tricky here. I'm rewriting middle term as two like terms based on the factorization of AC. All right. So this is again the most important step in the computation. Rewrite, replace that middle term by, this factor times x plus this factor times x. All right. Now group the first two terms, group the last two terms, and do what you did in the first example. Take the common factor out. All right. Between these two terms, common factor is 1 power of x. I pull it out. Leftover is 1 power of x from the first term, 4 from the second term. Yeah. Between these two terms, common factor is 3. So I'm going to pull 3 out. Leftover is x minus 4 in the parenthesis. Now, as I said, as a product altogether, this is one term. This is second term. So see, we converted 4 term into 2 terms by, grouping the first two and last two term and taking common factor out, right? Now, I want you to focus on these two terms only. Is there any common factor? Answer is yes. Look, x minus 4 appears as a factor in both terms. And by the way, if your work is correct, you will get the same thing in the parenthesis. All right? Take that x minus 4 out. If you factor x minus 4 out from here, leftover is x. If you factor x minus 4 out from the second term, leftover is plus 3. And this is really the full factorization of the trinomial. Now think about that general process that I gave you. This is that general method in form of a particular example. Compute product of A and C. Find the factors of A and C whose sum is B. Break the middle term into two pieces based on the factors of AC. Group the first two, group the last two terms. Take the common factor out from first to last two terms, and then take the common factor out one more time. You are done. All right. So that's basically the whole deal. Now let me mention here that this work is really the side work. You don't have to show this work in your computation. You don't have to include this part in your computation. This is a side work. What you need to show is these 3 lines only. This is your solution. This is the only work to be included in your solution of factorizing this trinomial. All right. So again, keep in mind, fairly simple process. There is no real trick here. I also would like to mention some of you may have heard a word, monic polynomial. Right? Let me tell you what is monic polynomial. Polynomial is monic if the leading coefficient is 1. If the leading coefficient is 1, I would call the polynomial monic polynomial. You may wonder that why did I mention this word? I will tell you. I will give you this answer in next 5 minutes. But for now, keep this word in mind. Monic polynomial. Polynomial is monic if the leading coefficient is 1. If the leading coefficient is other than 1, it's not monic. For example, this is not a monic polynomial because leading coefficient is not 1. This is not a monic polynomial because the leading coefficient is not 1. Let's try to go to the next example now. Now remember, we can create an example which uses both first and second method together, right? This is a perfect example to demonstrate that. There are 3 terms here, 1, 2, and 3. Look for the common factor first. Between the numbers 8, 4, and 12, 4 is a common factor. Between the power of x, looks like x square is a common factor, right? 4x square is what I would like to pull out. Let's do that. I'm going to factor 4x square out from the first term. 4 is being taken out as a factor. Left over is 2 and then x square. 4x square is being taken out, so 1 power of x is left over. 4 is being taken out as a factor, 3 is left over. All right. I want you to notice that inside the parenthesis you have a trinomial. All right. You need to worry that can we factorize this trinomial any further? If yes, then we would like to go ahead and factor it out. If not, then that is our final answer. Let's check if we can factorize this any further. Okay, so I have a equal to 2, b is -1, and c is -3. These are the values of a, b, and c. I'm going to do this side work in one corner now. It's not a part of our solution, so let's do it on the side. Okay, so I got a, b, and c value. What is a times c? Well, a times c is 2 times -3, and this is -6. All right. I would like to find out, I would like to see if there are any factors of -6 that I can add and get -1 as a result. Let's write down all factors of -6. -1 times 6, -6 times 1, -2 times 3, -3 times 2. Is there any of this that adds up to -1? Answer should be yes. There is one factor that adds up to -1. One set that adds up to -1. -3 plus 2, it's -1, right? So we can factorize this polynomial further, right? So these 3 are ruled out. Let's break that middle term into 2 pieces. 2x square minus 3x plus 2x. So I get minus 3x plus 2x minus 3. So I converted 3 terms into 4 terms by rewriting middle term as a sum of 2 like terms based on the factors of AC. All right. Okay, so I group the first 2 and last 2 terms. Time to take the common factor out. Let me use the bracket here. So between the first 2 terms, x is the common factor. If you pull it out, left over is 2x plus 2x minus 3 in the parenthesis. Now there is nothing common between these 2 terms, so we can assume that the common factor is 1 there. Right? So we factor 1 out. Again, as I said last time, if you get the same thing in the parenthesis, then that means you are on the right track. Your work is correct. All right. Factor 2x minus 3 out and you are done. Look, 4x squared, 2x minus 3. Left over from that first term is just x. Left over from the last term is just 1. Done. This is full factorization of given polynomial. All right, so again, my intention was to demonstrate how we can use the first two stages of factorization all together in one single example. And that third example is a perfect example to demonstrate that. Okay. As I said, most of you should have seen this thing in the past. Now, the question that I told you that I'm going to answer, it's time to answer that. Why did I mention the monic polynomial? The reason I mentioned the monic polynomial is this, that for monic polynomial, you can factorize it directly. You don't have to go through breakdown of the middle term into two pieces. All right. So again, if the polynomial is monic, we can write down the factorization directly. Let me show you how. Okay. So I'm going to. Okay. I need this. So let me keep this thing here. Okay. So here is the same monic polynomial, x squared minus x minus 12. All right. Coefficient of x squared term is 1. And I'm saying that I have a shortcut to find out its factorization. And that shortcut will be following. Find the factors of negative 12 whose sum is negative 1. So you still have to do this work in your mind. All right. So we have the factors negative 4 and 3 whose sum is negative 1. Right. So negative 4 times 3. This is really the set of factors that adds up to negative 1. Let me show you how I am going to write down the final answer. The final answer will be x plus first factor, x plus second factor. Look, x plus negative 4, x plus positive 3. All right, and that is your complete factorization. Look, I wrote it in just one line. Look at this. I skipped these two steps where I did the breakdown of the middle term into two pieces and then factoring things out. The reason why I'm mentioning this is because in this course you are going to deal with monic polynomials so frequently, and you don't want to write down those additional lines all the time, right? I'm sure that many of you must have seen this in the past. I just wanted to recall the idea. This can be done only if the polynomial is monic. Let's try one more. Okay, so let's say I ask you to factorize x squared plus 7x plus 10. Okay, the first question you would like to ask is this: is the polynomial monic? Is the coefficient of x squared 1? Answer is yes. Meaning, if there is a factorization, it can be done in one line, right? Okay, now second question. Do you know any factors of 10 whose sum is 7? Well, what are the factors of 10? 10 times 1, negative 10 times negative 1, 2 times 5, and negative 2 times negative 5. Is any of them add up to 7? You would say 2 and 5, right? Positive 2 and positive 5, they adds up to 7. The factorization would be x plus 5, x plus 2, plus 5 plus 2. These are the two factors that I had, right? And again, be very, very cautious, very, very careful. This technique can only be used when coefficient of x square term is 1. You cannot use that technique in this example. Look, coefficient of x square term was 2. This is not monic polynomial after I take the common factor out. All right, and that's why I have to go through, full 3-line computation. 3-line computation is not that bad, but you can do this computation in just 1 line for few special cases, and those few special cases, they have to involve monic polynomials. Okay, all right, so let's keep this thing in mind. Let's try to solve that example number 7 now. Again, this is a side work. You don't have to show this in your solution. In your solution, you only have to write these 3 lines, and that's pretty much it. If the polynomial is monic, go ahead and write the answer directly in 1 line. Perfectly fine to do that. Okay, so let's try. Example number 7 now, which uses spatial factorization formulas. And as I say, there is nothing really tricky about spatial factorization formulas. I'm going to write down those 2 sub problems here side by side, and then we will solve them carefully. The first one, it says x to the power 4 minus 81 y to the power 4. And the second one is x to the 3 minus 8. Okay. All right. The idea remains the same. Okay, I am going to, there are only 2 terms. I look for the greatest common factor. There is nothing common between these 2 terms, right? So we really don't need to apply the first stage of factorization. This is not a trinomial. So technically, I can't really, I rule out that second stage as well. That leaves me with this final choice. All right, spatial factorization formula. Can we factorize this using spatial factorization formula? If yes, then use it. If no, then that means we are dealing with something that is non-factorizable. All right? Okay. Let's try this carefully. There are only 2 terms. I have 3 formulas that has 2 terms in it. The first one got 2 terms. Fourth formula, sum of 2 cubes, difference of 2 cubes. These are the 3 formulas that has 2 terms in it. So meaning I rule out formula number 2 and 3. Okay. Now the sign in between these 2 terms is negative, right? So that will help you rule out formula number 4 as well. So now I know that if this is factorizable, it must be, I must use either formula number 1, which is difference of 2 squares, or formula number 5, which is difference of 2 cubes, right? Okay, so which one should I use? For that, I want to ask you a very simple question, all right? And that simple question will answer immediately. Which formula should we use? All right? Now, here is that question. Do you know the square root of each of these terms, these 2 terms? And if this square root is clean means it does not involve any radicals. All right? So square root of x to the power 4 is x squared. Square root of 81 y to the 4 is 9y squared, right? These are clean square roots. All right? So we know the square root of both of these terms. All right? Do we know the cube root of both of these terms? And are the cube root clean? Well, cube root of x to the 4, we don't know it, right? So technically, you see, that question rule out the last formula as well. These two terms can be visualized as a difference of two squares, not difference of two cubes, right? And I ask a simple question that do we know the square root of this term or cube root of this term? Answer was simple. We know the square root of this term. So obviously difference of two square formulas tend to be used. Let's do it. So I'm going to write down this as a difference of two squares. What goes in the parenthesis is a square root of each of this term. What's the square root of x to the 4? X squared. Square root of 81 is 9. Square root of y to the 4 is y squared. Look, this is your a, this is your b. Write down the factorization as a minus b, a plus b. Okay, let's do it. A minus b, a plus b. It's a good habit to speak, the formula while you are solving the example. This will make the idea very clear in your mind. Okay, so a minus b, a plus b. So first factor minus second factor, first factor plus second factor. This is the factorization I got. I see the squares in both of them. So one more question. Is there any common factor between these two terms? Answer is no. This is not a trinomial either. Now next question is, can I factor this further using these formulas? Well, there are only two terms with negative sign in between, first or 5, right? The question is, do we know the square root of this or cube root of this? We know the square root of this, meaning I can use difference of two square formula here. Again, write this in form of difference of two squares. Obviously, I will do x minus 3y, x plus 3y to factorize this portion. How about that? Let's do that one too. Okay. So again, there are only two terms with positive sign in between. All right. Two terms with positive sign in between will rule out formula number 1 and 5. I only got one formula left, and that's the sum of two cubes. A cube plus b cube. This is the only formula I have. So the question you would like to ask is, does this term has a clean cube root? Answer is no, meaning I cannot use this factorization formula. All right, so this thing is non-factorizable. This portion is a non-factorizable. Leave it alone, right? So let's factorize this and we are done. X minus 3y, x plus 3y, and then x squared plus 9y squared. Done. This is a full factorization of this polynomial. All right. So again, there is no trick here. You just have to find out the correct matching formula using your own logic. And once you find the correct formula, you can use the formula to factorize it. Let's check this one. Only two terms, no common factor. This is not a trinomial. Two terms with negative sign in between. There are only two formulas, 1 and 5. Difference of two square, difference of two cubes. Question you would like to ask is this. Do we know the square root of this or cube root of this? Which one is clean? Obviously, cube root of this is known, meaning I must use difference of two cube formula here. Well, I'm going to write this as a difference of two cubes. What goes in the first parenthesis is a cube root of x cubed, and cube root of 8 will go in the second parenthesis. A minus b, a square plus ab plus b square. Let's simplify that. A square plus ab plus b square. Now let me mention to you here that do not try to factorize this. This is a non-factorizable trinomial. If it is factorizable, then I would have factored it here and simplified it further, right? Check it. All right. This is a monic polynomial. Do you know any factors of 4 that adds up to 2? The factors of 4 are 2 into 2, negative 2 into negative 2, 4 into 1, negative 4 into negative 1. Sum of this is 4, negative 4, negative 5, 5. None of them adds up to 2. Meaning, I can't factorize this trinomial any further. This is really an example of non-factorizable trinomial. Okay, so understand that that part is non-factorizable. Now, as I said, I use the wording that we need the concept of factorization in order to divide a polynomial by polynomial. Let me give you one illustration to demonstrate this. Let me clear this out quickly. Let me remind you this idea with something that is very well known to you. Think about it. Think about this example. 4 divided by 6. If I ask you what is 4 divided by 6, you will immediately say 2 over 3, right? Now I want you to go back and think about it. How did you get 2 over 3? You must have done this in your mind. It's really like we are doing this so frequently, and that's why the answer is almost immediate. You must have factorized 4. You must have factorized 6. You must have crossed the repeating factor out from top and the bottom to get that, right? So we can do exactly the same thing with polynomials as well. Look, here is an example. Suppose I give you x squared minus x minus 6 divided by x squared minus 4. If I ask you to divide these two polynomials, what would you do? Well, same route, factorize top and the bottom polynomial completely, right? Do we know the factors of negative 6 whose sum is negative 1? Answer should be yes. Negative 3 and positive 2. Can I write down the factorization directly? Answer would be yes, because the polynomial is monic, right? X minus 3, x plus 2 is a complete factorization of the top. This is a difference of two squares, right? X square minus 2 square. Look at this. Repeating factor is gone. So this is what I meant by, division of two polynomial requires concept of factorization. You need factorization to handle the division. All right? Okay, now here is another interesting question. It's clear that we may have a situation where we have polynomial divided by polynomial, right? So the question is, if I give you two rational expression involving polynomials, is it possible to add them, subtract them, multiply them, and divide them? Answer to all these questions are yes. All right, so let's try to see this carefully. Okay, so here are few properties of rational expression. Suppose I give you 4 rational expression p, q, r, and s, be any rational expressions, right? In order to add two rational expressions, suppose I give you p over q plus r over q. How do you add two rational expression? Well, you would find the common denominator, right? And if the denominator is the same under both terms, then you are gonna perform this operation on the top expression. Here is one simple example. Let's say I give you 2 over 3 plus 5 over 3. How do we add these two numbers? Well, since the denominator is same under both rational numbers, I would write this as a common denominator. And what I would do is I would just apply this plus operation on the expression sitting in the top, right? I end up getting 7 over 3, right? And this 7 over 3 indeed is, the final answer. The question is, can we do this with the polynomials too? If you have two rational polynomials, two rational expression involving polynomials with the same denominator, can we just add the polynomials in the top to simplify it? Answer is yes, we can do this. All right. So fairly simple deal here. What about subtraction? Well, if you have P over Q minus R over Q, two rational expressions sharing the same denominator, all you have to do is subtract expression sitting in the numerator, and write Q as a denominator. All right. What if the denominator is not the same? Suppose you have P over Q plus R over S. Let's say you have 2 over 3 plus, 7 over 5. All right. If this is the case, then what you do here is you find the common denominator of common multiple of 3 and 5, least common multiple of 3 and 5. The least common multiple of 3 and 5 is really 15, right? You will have to make 15 visible under the first term and under the second term. To make 15 visible under the first term, you're going to multiply and divide this expression, the first rational expression, by 5, and you are going to multiply and divide the second rational expression by 3 in order to make denominator 15. My goal is very clear. See, I want the denominator to be same. So what I get here is 10 over 15, right? And then for the second term, I get 21 over 15. Now look, this form is exactly same as that first formula, right? You have the same denominator in both rational expression. Write 15 as a common denominator and simply apply this addition operation on the expression sitting in the top, right? So you really get, 10 plus 21, which is 31 divided by 15, right? Question is, can we do this with polynomials? Answer is yes, we can do this with polynomials as well. Okay, so this is the, see, I multiply the common denominator is really QS. I multiply and divide the first rational expression by the missing factor S in the top and the bottom, and I multiply and divide the second rational expression by the missing factor, which is Q, right? PS plus RQ over QS. That's what we get, right? Now, let's talk about multiplication and division, which are rather simple. How do we multiply two rational numbers? Let's say 2 over 3 and 5 over 7 maybe, right? How do we multiply two rational numbers? Well, simple. Multiply top with top, bottom with bottom. So multiplication is indeed a simple process. 10 over 21, and that's what we did. Division is also simple. P over Q divided by R over S, right? You can convert this division into multiplication by simply multiplying first rational expression by the reciprocal of the second rational expression, right? So P over Q divided by R over S is really PS over QR. And then last but not least, the property that I just showed you, right? If you have a common factor between top and the bottom expression, you can cross it out and you can simplify it as P over Q. All right. Okay, so keeping this in mind, let me give you the general strategy to add, subtract, multiply, and divide rational expressions, or to simplify the rational expression. Again, this is just a general framework. Once it is done, I am going to show you series of examples to support it, right? To simplify rational expression, we should use factorization. Remember, factorization is a key part here, okay? To add and subtract rational expression, I will have to do the following. Number one, factorize the expression in the denominator completely, if possible. Find the common denominator. Make the common denominator visible under each rational expression by simply multiplying and dividing each term by the missing factor, right? And once the common denominator is same under all terms, perform the given operation on the expression in the numerator. All right, so these are the steps that you need to follow in order to add or subtract two rational expressions. All right. Multiplication and divisions are simple, right? To multiply and divide rational expression, just factorize them and then cross out, repeating factors from top and the bottom of each expression, right? As I said, I would like to show you three examples. Example number one is a numerical example demonstrating sum and difference of two polynomials. Sorry, rational expression involving polynomials. And then number three is multiplication and division of two rational expression involving polynomials. Now, number three is the simplest example. So let me begin this computation by showing you number three first. All right, so we are going to solve number three, problem 1 and 2, A and B first, and then I will go back and show you the solution of problem 4, problem 1 and 2, all four sub problems. All right, so let's do this work on the board. So let me clear this quickly. All right, so here is example number 3 from today's handout, the last example that we are going to do first. I have x squared minus 5x plus 6 divided by x squared minus 7x plus 10. So this is the first rational expression. You would like to multiply it by x squared minus 25 divided by x squared plus 5x. All right. And then the second one is x4 minus 16 divided by x squared plus 4. And this is divided by x minus 2 over x. Okay, let's do these two examples one by one. As I said, these are perhaps the simplest example. If you know factorization, these examples are kind of straightforward. I'm going to factorize each of these four expressions. Let's do this on a side. Okay, so I'm going to factorize x squared minus 5x plus 6 first. Do we know any factors of 6 whose sum is negative 5? Answer should be yes, negative 2 and negative 3. The second question, can I write down the factorization directly? Answer is yes. Why? Because the polynomial is monic, right? X minus 3, x minus 2 is the complete factorization. All right. Again, the polynomial is monic. That's why I am able to write down the factorization directly. Okay, how about x squared minus 7x plus 10? Factors of 10 whose sum is negative 7, and this is a monic polynomial. Negative 5 and negative 2, right? So x minus 5, x minus 2, or x minus 2 and x minus 5. All right, x square minus 25. Looks like this is a difference of two squares. X square minus 5 square. X minus 5, x plus 5. And then x square plus 5x. This has got only two terms. Look for the greatest common factor, pull it out, and done. I got factorization form of all these four polynomials. Let's replace those polynomials by their factors. This is x minus 3x minus 2, x minus 5, x minus 2, and then x plus 5, x minus 5, and then x times x plus 5. Let's cross out the repeating factors. Looks like three factors from the top, three factors from the bottom are gone. I only left with one factor in the top, which is x minus 3, one factor in the bottom, which is x. And that's it. This is the simplification of that product of two rational expression. Let's do the same trick. In the second example, I'm going to change that division sign into multiplication sign. So let's write down next step first. If you want to change this to multiplication, you will have to multiply first rational expression by the reciprocal of the second one, right? Okay. I need full factorization of all of them. These two, they are already in the factor form. X to the 4 minus 16 looks like difference of two squares, right? X square square minus 4 square. This is x square minus 4, x square plus 4. As you know, we can factor x square minus 4 further as x minus 2x plus 2. And then I have x square plus 4, which is non-factorizable part. This problem is similar to what we did earlier, all right? It gives you a feeling that x square plus 4 is, if it's pretty clear that x square plus 4 is non-factorizable, so I wouldn't try to factorize this. X minus 2x plus 2, x square plus 4, that's the factorization of the top, x square plus 4 in the bottom, times x over x minus 2. Let's get rid of the repeating factors. All right, looks like I end up getting x times x plus 1, x plus 2 in the top with 1 in the bottom, right? This is the simplification of that second problem, second subproblem of number 3. By now, it should be clear that the more you practice factorization, more easier this example will be, right? Okay, now let's move on and let's try to do example number 1 and 2. Each subproblem, one by one. All right. So let's talk about addition and subtraction in the remaining 10 minutes. So let me clear this. You will see how nicely these problems are constructed. Okay, so here is the first subproblem from example number 1. I want to add 3 over 7 and 2 over 7, right? Okay, how do we add them? Well, we check the denominator first. Denominator in both terms are the same, right? So 7 is the common denominator. It is already there under the both terms. So all I'm going to do is, perform this operation on the expression in the top. All right. Again, intentionally, I'm using the word operation You may have addition or subtraction there. 3 plus 2, 5 over 7. All right, so this is the first sub-problem of example number 1. Now let me write down the first sub-problem of example number 2 right below it. So example 2, first sub-problem, it says I would like to add 5x plus 3 over x plus 5 with 2x minus 7 over x plus 5. Now think about it just for a second. How did I create this example? Well, I replaced 3 by 5x plus 3, 7 by x plus 5, and 2 by 2x minus 7. That's how I created this example. Again, strategy should remain the same. Look at the denominator. It's the same under both rational expression. I can write x minus 5 as a common denominator. All I have to do is perform this addition operation between expression in the top. I strongly encourage you guys to write both expression in the parenthesis initially. The reason will be very clear when you see the second example. All right. Let's open the parenthesis. This is a sum of two polynomials. We know how to add two polynomials, right? Just add the like terms. 5x plus 2x, 7x. 3 minus 7, negative 4 over x plus 5. Done. So you see, so logically, these two problems, they are indeed the same problem. The only difference is I used numbers in the first problem and I used the polynomials in the second problem, right? Let's try sub-problem 2 in example number 1, which is about subtraction. 3 over 7 minus 2 over 7. Again, denominator is the same. I'm going to perform subtraction on expression sitting in the top. All right. Sub problem B in the second problem. Look, I have 4x minus 3 over x plus 6 minus 5x plus 2 over x plus 6. Similar situation, right? Subtraction of two rational expression with the same denominator. All right. What do we want to do? Well, write x minus x plus 6 as a common denominator, and then we try to perform subtraction on the expression sitting in the top. Again, I strongly recommend you guys to write both expression in the top in the parenthesis. The reason will be clear now. When you distribute negative sign, the sign of both terms will be flipped. All right. So this will eliminate the chances of sign errors, which are so frequent in this course. 4x minus 5x, negative x, negative 3 minus 2, negative 5. And I got x plus 6 in the bottom. All right. Let's try the third sub-problem, which is, slightly more delicate case. 3 by 2 plus 5 by 7. All right. How would we handle this? Well, we realize that the denominator in both rational expression is different, right? I need to find out the least common multiple of 2 and 7. What is the common multiple of 2 and 7? 14. Make 14 visible under the first term. Look, factor 2 is already there. Missing factor is 7, so multiply and divide it by 7. Factor 7 is already there under the second term. 2 is missing, so I would multiply and divide, that second number by 2. Look, 3 times 7, 21 over 14 plus 10 over 14. Now the denominator is the same under both terms. We make that example look like number 1. All I have to do is perform this operation on the expression in the top. Looks like 31 over 14 is what I get. Right? Need to do the same thing to solve third subproblem in example number 2. All right, and this will be the final problem for today. I have x plus 4 over x plus 3 plus x plus 5 over x plus 1. All right, we are going to do the same trick. The common denominator is a product of x plus 1 and x plus 3. I want that product in the denominator in order to make the denominator same so that I can simplify numerator. Let's do it. The missing factor under the first term is x plus 1, right? The common denominator is the product of these two. X plus 1 is missing under the first term. X plus 3 is missing under the second term. So I'm going to multiply and divide the second term by x plus 3. All right. Okay, so denominator is the same under both terms. I can write this x plus 3 times x plus 1 as a common denominator. What is in the top? Well, in the top I have x plus 4 times x plus 1, x plus 5 times x plus 3. What did we do with these numbers in the top? We multiplied them, right? So do we know how to multiply two polynomials? Answer should be yes, right? Remember the FOIL method? Let's FOIL this out. Okay, because I need to eventually add two polynomials in the top, I will have to multiply both of them and then addition will be performed. Let's FOIL it. X squared plus x plus 4x plus 4, x squared plus 3x plus 5x plus 15, and then all over x plus 3, x plus 1. There are series of like terms here. Simplify them. X squared plus x squared, 2x squared. Then I have 5x plus 8x. 5 plus 8, 13x. And then I have 4 plus 15, which is 19, over x plus 3, x plus 1. And that's indeed the end of the story. That is really, the final answer. That's how far we can simplify. Now, what I recommend you guys to do is try to do the fourth sub-problem of example number 1 and fourth sub-problem of example number 2. When we meet next time, I will definitely go ahead and show you the solution of fourth sub-problem of example 1 and 2. But I want you guys